So this is dm. So therefore, dmg is the force on it. So in equilibrium,
these two are equal.
in equilibrium, those two have to be equal in magnitude. They have to add to 0. So the pressure force is minus dpdr times rho a dr, and the gravity force is minus rho g times a dr. Those have to add up to 0. And notice that rho a and dr appear on all three terms, so we can divide through by those. And so we find that dpdr is equal to minus rho g is equal to minus g m sub r over r squared times rho. And that is equation 1, the equation of hydrostatic equilibrium.
If you divide it by rho ADR, then how?
Oh, that's because it didn't belong there. It was just dpdr, adr.
Yeah.
Sorry, so I'm dividing through by ADR. Thank you, yes, ADR, yes. Oops. Yeah, rho is not in the pressure.
Pretty cool. Like the derivation.
Yeah, it's a nice derivation. It's you can make a picture, so to speak. So since rho and m of r and r squared and g, those are all positive numbers, notice dpdr is negative. In other words, pressure decreases outwards, which means the pressure gets higher and higher the deeper you go inside the star.
Which makes sense.
Yep. So I'll turn that around and say pressure increases inwards. The deeper you go in the star, the higher the pressure. It has to be because you need the pressure on the bottom of the layer to be higher than the pressure on the top of the layer.
Just like in at sea levels of pressure.
Right, the pressure is lower in Earth's atmosphere than it is high up because in any given layer, the pressure has to be stronger on the bottom of the layer than on the top in order for there to be enough upward pressure force that exactly balances the weight of the layer, that little chunk. So that's equation 1. Equation 2 is really easy to derive as well. Equation 2 is the equation of mass continuity. Mass continuity. Yep. So in other words, while it might be obvious to us, you have to tell a computer this if you're going to make a stellar model. Suppose I have a shell, a spherical shell within the star, and the shell is of radius r and thickness dr. And let's say m sub r is the mass interior to radius r. Then the mass of the shell will be the extra increment in m sub r that is inside radius r plus dr. So dm of r, m of r plus dm of r is how much mass is interior to radius r plus dr. Okay, that's the idea here. And it must be that dm of r is the density at that radius times the volume of the shell. What's the volume of that shell? Think in terms of calculus. So it's certainly, you could do it as 4/3 pi r plus dr cubed minus 4/3 pi r cubed, but let's make an approximation. The volume should be the area times the thickness. So what's the area?
Pi r squared.
Not pi r squared, but it's a sphere. So pi r squared is a
4
circle.
pi r squared.
4 pi r squared times dr.
Because it's a spherical shell.
Because it's a spherical shell. That's right, it's a spherical shell. So dm of r is rho times 4 pi r squared dr.
Where rho is the local density? And
Rho is the local density. It's rho in the shell. So it's rho at radius r, in other words.
Sweet.
So this says that dm of r dr is 4 pi r squared rho. And that is equation 2. That's the equation of mass continuity. Boom.
Oh, geez, that was fast.
Yep.
I did not expect that.
Right.
Oh, so this describes how mass changes
With radius, yeah. It's how the mass interior to radius r changes with r. And so again, it's pretty obvious, but you have to put that in the math. It has to be built in. So that's another differential equation that our star model has to satisfy. So far we've got 2 equations. We're going to have 4 of them, and then another one that's called a constitutive relation. Let's get equation number 3 today, and then we'll be done, because it's another quickie. So this one is the equation that describes energy generation. We're going to let epsilon, which has 2 pieces, epsilon nuclear plus epsilon gravity, be the energy generated per kilogram in a spherical shell. So if we're in the core of the star where nuclear reactions are happening, epsilon will be the energy generated per kilogram by nuclear reactions at that radius away from the center. The star could also be shrinking or expanding and converting via the virial theorem gravitational potential energy into thermal energy and radiation. So we also need epsilon gravity contribution. So epsilon, which is the sum of those 2 contributions, And if the star isn't shrinking or expanding, it'll all be epsilon nuclear. Let that be the energy generated per kilogram in a spherical shell at radius r. Actually, I gotta be careful. I should really say the power generated per kilogram. Yeah, the energy per second per kilogram. I have energy in my notes, but it's better to say power. So the power generated in the shell contributes dL sub r to L sub r, where L sub r is the luminosity emerging from the surface of the shell. L sub r is the luminosity emerging from the surface of the shell of radius r. So the idea here, let's say that's where all the fusion is happening, inside the core. Then L sub r, if this is radius r here, L sub r, the total power coming out of that spherical shell, if we're in equilibrium, has to equal the total rate that energy is being generated inside that shell. And this is what this equation describes. What it says is the extra contribution to L sub r coming from a shell like this one. In other words, the extra luminosity coming at r plus dr compared to r is equal to how much power is being generated within that shell.
Sure.
Otherwise, you wouldn't be in equilibrium. So dLr would be equal to the energy generation rate per kilogram times the density times the volume of the shell, 4 pi r squared dr. In other words, this is the mass of the shell, that times the energy generation rate per kilogram is the increment to the luminosity produced inside that shell. That's the power being generated inside that shell. So now we just divide through by dr again, and we already have our third equation. The L sub r dr is epsilon times 4 pi r squared rho. So notice how similar equations 2 and 3 are.
With an additional factor.
All you got is an extra epsilon to say that, okay, there's a little increment in mass given by 4 pi r squared rho, multiply it by epsilon, and you get the little increment in luminosity due to energy generation inside that shell. So in a star like the sun, dLdr is positive until you get out of the region where nuclear energy is being generated, and then luminosity stays constant because there's no power being generated in the sun's outer layers. force.
Yeah, I guess if you move far.
Yeah. If you're out of the energy generation region, epsilon is 0. You're not generating anything anymore. And so the luminosity is constant once you get outside of the sun's core. The total amount of energy flowing into any shell is equal to the energy flowing out of the shell. But in the core, the energy flowing into the bottom of the shell plus the energy generated inside the shell in each second equals how much energy is coming out of the top of the shell, the outer edge of the shell. So we've already got 3 of the 4 equations, and it's going to take as long to get the 4th equation as it did to get all these combined. Because it's more complicated. The 4th one, which we'll do next time, is the equation of energy transport. And we have to take into account that it could be radiative or convective, and so there's 2 different cases we have to.
I think I remember you showed it to us over the summer. And
Probably
you
did,
said-
yeah.
and you-
Right. There's a slide that says, there's a slide from one of the intro textbooks that shows the equations of stellar structure. And so when I'm teaching it to intro astronomy, I'll mention, yeah, if you want to see where these come from, take Astronomy 310. And only the students who want to major in astrophysics ever take me up on that. No matter how hard I say, come on, it'll be fun. Like, no,